And again, this is something that was taught pretty much the same way in Algebra 2. There shouldn't be a lot new that's going on with this. Geometric, right? What's a geometric sequence? Okay. Right. We know what arithmetic means. Arithmetic means you keep adding the same number to get the next term. What does geometric mean? You keep multiplying, right? So geometric is a multiply. The geometric sequence. And here we talk about the ratio of consecutive terms, meaning divide one term by the term that went before it. And you should do that for every number in the sequence. You keep doing that. And if every time you get the same number, the same ratio, then that's called a common ratio. Right? Here they're showing A2 over A1, A3 over A2, A4 over A3. Right? Every time you keep getting the same number, that means you have a geometric sequence. Good. Hannah? You done, Hannah? Okay. So, I mean, these are examples of geometric sequences. I mean, it's not, is it geometric? They're telling you it's geometric. They're just showing you what it looks like when it's geometric. Right? Notice in this one here, 2, 4, 8, 16. I mean, if I didn't give it a name, you'd see the pattern, right? What's the term that comes after 16? 32. And after 32, 64. I mean, you recognize it. Okay. Now, if you did the test for geometric, right, you'd be doing 4 divided by 2, 2. 8 divided by 4, 2. 16 divided by 8, 2. In every case, right, you get the same thing. So that is the common ratio, 2. Right? And again, just like this is like an analogous example to the one we started with for the arithmetic. And then you have a formula for the nth term in the sequence. And do you see in that formula the common ratio? Yeah, I mean 2 to the n. I mean, unlike the arithmetic, the formula looks kind of linear, right? The n is to the first power. For a geometric, it looks exponential. The n is in the exponent. That's what makes it geometric, right? And whatever it is that's being raised to a power, that's the r. Right? That's why, because every time you increment n by 1, you get one more factor of that number, whatever it is. Right? Look at this one here. 12 to 36. Okay, well, right away you're going to say that's 3. 12 times 3 is 36. 36 over 12 is 3. So 108 over 36 is 3. These are numbers we wouldn't really have rolling around our brain. Not like that, which we clearly recognize. 324 over 108. Every one you can verify. Okay, this is the same number every time, which means it's geometric, and that's the r. Okay, now look at the formula again for a sub n. Right? Do we see our common ratio? Common ratio is 3. There's the 3. It's the thing that's being raised to the n power. And the last one, even with fractions, right? Even with fractions and even with terms changing signs, right? We have negative 1/3, positive 1/9, negative 1/27, positive 1 over 81. I mean, do you see the pattern in terms of the denominator? 3 to 9 to 27 to 81. Yeah. So the R is negative 1/3. And if I looked at the formula for A sub n, I see the R, it's what's being raised to the power, right? And just like when we did our formulas in 9.1, right, what was it that made the terms of the sequence change sign? It was raising a negative to a power, right? That meant every time you change, when n goes from an odd to an even, you just change the sign, right? And now it's positive or now it's negative. So that's a geometric. Geometric, okay? And we have, just like we did with arithmetic, we have a formula for the nth term of the sequence. And this is the same formula that we used before. A sub n equals A1 times R to the n minus 1. So we recognize the parts of that formula. The A1 is the first term, the R is the common ratio, right? The n is the ordinal number of that term, like which number term is it in the sequence. Okay. Using that formula, if I want to find the first term, then what would n equal? 1, right? If I substitute n equals 1, notice what happens. Right? Then I get A1 equals A1 R to the 1 minus 1, which is A1 R to the 0. And what is anything to the 0 power? 1. Right? So basically A1 equals A1, which is better. But that's why the exponent here has to be n minus 1. It's not just n, it's n minus 1. Right? And that makes whatever is this number in front of the R, that's the first term. Okay, so that's our nth term of the sequence. Same formula you had from last year. So writing terms of a geometric sequence, in this case, we know the A1 and we know the R. So do we need that formula to find the first 5 terms of the sequence? Or if you know the first term, and if you know the R is 2, then what's the second term? 3 times 2, 6, right? What would be the next term? 12, right? And what is the next term? 24. What is the next term? 48. So 1, 2, 3, 4, 5. It's not like you got to go back to that formula and do it 5 times, right? Just take the first term and double it and double it and double it and double it. Okay, find the 15th term of a geometric sequence whose first term is 20 and whose common ratio is 1.05. Ooh. Now, do you think that we want to go, okay, here's the first term, that's 20, and then our second term is going to be 20 times 1.05, and keep multiplying it times 1.05? I think that's going to get kind of hairy. How about instead we just use the formula? I mean, this is a place where you probably just want to use the formula, right? Because to multiply times 1.05 20 times, you know, that's just going to have all kinds of decimals floating around. Why not use this? AN equals A1 R to the n minus 1. Okay, so we want A20. The first term is 20. No, sorry, we want the 15th term. I knew I was messing that up. We want A15. The first term is 20, and then we've got 1.05 to the 15 minus 1. And that you can just put in the calculator. And the answer is 39.599. That's a lot easier than 15 times multiplying times 1.05 to get where you're going. Use the formula. We're good. Okay. Find the 12th term of the geometric sequence. Okay. So let's see. We could do this in both ways, right? You could just like figure out what's the common ratio and keep multiplying until you get there, or you can use the formula, right? If we use the formula, right, an equals a1 r to the n minus 1, then what things do I need to plug in? First term, common ratio, and then the ordinal number of that term. You're at 12. We've got them all. I mean, it's all pretty much right in front of you anyways. Right? What is the R? 15 over 5 is 3. So that's, we pretty much have everything. I mean, if you want, you could multiply times that 3 9 more times and get there. I'd prefer to use the formula. Right? A12 equals A1, which I can see, R, which is 3, raised to the 12 minus 1. A12 equals. A12 equals. And here's my calculator. Here. 5 times 3 hat 11. 885,735. Now, when you deal with that formula, don't do this. Don't try to multiply 5 times 3 and get 15. You can't do that. Okay, that's going to be a fundamental error, right? It's not much to grade after that point. Right? You can't put those together because 5 is not being raised to that power. Only the 3 is. Good. Okay, the 4th term of a sequence is 125, and the 10th term is 125 over 64. Find the 14th term. Alrighty, well, let's see what we got, just to like draw a picture of it in a way. The 4th term is 125. 4th term, 4, 5, 6, 7, 8, 9, 10. 10th term. So we know that this term is 125. And the 10th term is 125 over 64. You know, we got to find the 14th term. Right. So what one number do we need to know in order to do that? You need the R, right? I mean, if you knew that the R is, you could just multiply by this times that R once, twice, 3, 4 times, and you'd have it. Okay, so how can we figure out what the R is if we just have these two terms? How many times would you multiply times R to go from the 4th term to the 10th term? 6 times, right? The difference in the subscripts there, right? So we know that this 125 times R to the 6th equals 125 over 64. So that is something you can solve for the r, right? Divide both sides by 125. R to the 6 must be 1 over 64. Okay, so take the 6th root of both sides. R equals 1/2. Okay, so at this point, I mean, if you wanted to use the formula, you would have to okay, if you multiply times a half to get the next term, what would you multiply by to get the term before? Times 2, right? You could multiply 250, 500, 1,000. Now you got the first term and you've got the r, so you could use the formula. Or you can just, multiply this times r. How many times did you multiply times r to go from the 10th to the 14th term? 4 times, right? So we're going to go 125 over 64 times 1/2 to the 4th. Okay, and 1/2 to the 4th. 2 to the 4th is 16, so that's 125 over 64 times 1 over 16. And that is 125 over 1024. This idea, to go from one term to another, right? How many times you multiply times r? I mean, that is one of the things that you have to do and probably causes us a little more trouble. But again, to go from the 4th to the 10th, we did 6 times. To go from the 10th to the 14th, we did 4 times. Whatever is the difference in the ordinal number of that term. So that's probably all the just finding nth terms in the sequence. Okay, now we're talking about the sum, right? Just like we did with the arithmetic, you got a formula for the sum, the finite sum, or the sum of a finite geometric sequence. Means it's only a fixed number of terms. And again, this is a formula that you've had before, and if you can't read it for all that, it's this: Sn equals A1 times 1 minus r to the n over 1 minus r. Should be a little familiar, right? What are all the things we need to plug into that? We need to know the first term, we need to know the r, and we need to know the number of terms that we're adding up. Interestingly, unlike the arithmetic, we don't need to know the last term, which makes it in some ways easier, right? You're never going to get one of these where you don't know the last term, so you got to take a side step to figure it out so you can plug it into the formula. Now, the problem with doing this is sometimes this calculation can get kind of hard. But if you put it in the calculator, or put it in the calculator correctly, then it should work. So the sum of this finite geometric sequence. So using that formula, and I always write down whatever formula I'm going to use, I'm going to write it down first before I start plugging things into it. Right? Here's our formula. Sn equals A1 times 1 minus r to the n divided by 1 minus r. Okay, how do I find the first term? When I'm looking at this summation notation, we did this already, right? How did we find the first term when we were starting with that notation? We plugged in the bottom number, right? So in this case, the A1 is going to be 4 times 0.3 to the 1 minus 1, which is 4 times 0.3 to the 0, which is 4. It's almost always the case. If this index starts at 1 and the exponent is the index minus 1, then this thing right here, that is the first term. The 4 is the first term. Right? So we got the A1. Okay, what is the R? In this formula right here, what is it that represents R? 0.3, right? It's whatever is being raised to the power. So that's 0.3. And how many terms are we adding up? Right? It starts at 1 and it goes to 12. N equals 12. So that's everything you need to plug in. S12 equals first term is 4 times 1 minus 0.3 to the 12th divided by 1 minus 0.3. I'm going to open up my calculator here. Okay, so second plus 7. Okay, so I mean, I can put this in the calculator pretty much like it is, looking like this, right? 4 times parentheses. Okay, now this numerator here, that needs to be put in parentheses, right? 1 minus 0.3, 1 minus 0.3 raised to the 12th power. You can arrow out of that so that you can put the right parenthesis. That's going to be the end of this part right here. Now when you divide, then you do 1 minus parentheses, 1 minus 0.3. And as long as you've got the parentheses in the right place, that will work. Enter. And let's see if it's got a fraction. Enter, enter. No, 5.714. I mean, you just have to make sure that you use parentheses wherever you should. Or you could do this. If you remember this, this is like a new thing that we learned at the end of last year. You could use the fraction notation in the calculator. Right? If I'm going to put my 4 in, and I'm going to multiply it by this fraction. So I go alpha y equals 1, and, oh, that's wrong, clear. 4 times alpha y equals 1. See if it works better this time. Okay, there we go. And now I can put in the 1 minus 0.3 raised to the 12th. Arrow down to there, 1 minus 0.3. So then you don't need the parentheses because it's actually being done in the fraction. Same thing. Okay, now for geometric only, it is actually sometimes possible to add up an infinite number of terms. I mean, shouldn't say for geometric only, but as opposed to arithmetic. You can't add up an infinite number of terms in an arithmetic sequence and have it converge to a number, because every time you add one more number, you just changed it. Right? But when it comes to geometric, again, I always use the example of the board. Right? If I was walking from, or I'm going to do it here so I can see it on the screen. Let's say that from here to here is 1, right? This probably should have gone the other direction, but let's say I'm going to go from one end to the other by going halfway each time. So going halfway would put me in the middle. That would be 1/2. I would go half of that. That's another 1/4. I go half of that. That's another 1/8. Right? Every time, if I go halfway to the end, I just cut that in half. But am I ever going to actually get to that point right there? No, I'm going to get infinitely close, but I'm never going to touch it. It's like a function's graph approaching an asymptote. It'll get infinitely close, but it won't quite touch that point. But you would still say that the sum is converging to that value, whatever it is. Now, this formula looks pretty similar to the one we had before. And the reason is this. Notice that the terms in our sequence here, they went from 1/2 to 1/4 to 1/8. They're getting smaller. And it's when the terms are getting smaller, a geometric sequence will converge. So the requirement for being able to add up an infinite geometric series is this. The r's got to be less than 1, which means when you multiply to get the next term, the terms are getting smaller. As long as that's the case, then this thing will converge. Now, if you look at the formula, look at the finite formula that we already have. Sn equals A1 times 1 minus r to the n over 1 minus r. Right? If the r is less than 1, like in this case, the r was clearly 1/2. If you let n increase, so you're finding like the 1,000th term or the 1,000,000th term, 1/2 raised to a really big power is like 0, right? If you just take in your calculator 1/2 raised to the 1,000th, it's essentially 0. So what happens when you let the n approach infinity, that term itself goes to 0. And what's left of your formula is just this piece right there, which is that. It's just like you're getting rid of that r to the n term. Because the r is less than 1, it's approaching 0. Get rid of it. So here's a couple examples in the two different ways you might see this presented, right? For the first one, it's an infinite series. Remember what's a series? The series is the sum of a sequence. It's an infinite series because it is definitely a summation, and it's going to infinity, right? So now we have to say, is r less than 1? What is the value of r in that formula? 0.6. So r is less than 1. So that means we can use this formula. S equals A1 over 1 minus R. Okay, so we know what our R is. How do we find the first term? Plug in the lower limit, right? So plug in the 0. A1 equals 4 times 0.6. And this one, n is starting at 0, but the index is n. So you're still raising something to the 0 power. So the first term is 4. So there's not much to plug into this formula. Right? S equals 4 over 1 minus 0.6. Right? Which is 4 over 0.4, which is 10. Okay. Now, in this one, it's written out, right? The terms of the sequence that are being added up are been written out. It's infinite because of the dot, dot, dot at the end. So I need two things to feed this formula. I need the first term and I need the R. In this case, I got the first term. That's right here, right? A1. How do I find the R? You divide consecutive terms, right? So let's take our R. Our R will be 0.3 divided by 3. Right? Just dividing the second term by the first term. And that is 1/10 or 0.1. So that's all you need to plug in. First term and R. S equals 3 over 1 minus 0.1. S equals 3 over 0.9. And let's see. What is that? 3.3 repeating? 3 divided by 0.9. 3.3 repeating. You know, if you had left it as a fraction, like 1/10, then it would have looked like 10/3. So remember that you can't use that formula if the r is greater than 1. It's specifically if the absolute value of r is not less than 1. You know, what's the purpose of the absolute value? That tells you it could be a negative number, right? It could be like in between -1 and 1. That would be okay. -2 would not be okay. That would not count as being less than 1 because it's not the absolute value. It's not less than 1. But you got to make sure that the r is less than 1. In this case, 0.6, less than 1. In this case, even without knowing what r is, you can see the terms are getting smaller, so it's clearly less than 1. Right? So yes, you can use the formula. But you can get presented with these kinds of problems when that's not the case, and you're supposed to say, can't use the formula. Something like this. Wait till everybody's done. Okay. Like in this problem here, it's an infinite sum. What is the value of r? 2.1. Can't do it. It's greater than 1. Or actually, the way you'd probably see it written, it would probably say something like this. Doesn't converge. And then the last one, I mean, this one you could tell what the r is pretty easily. But the main thing is, do you notice that the terms are getting bigger? Yes. So r is greater than 1. Can't use the formula, right? Terms getting bigger. Right. Doesn't converge. Okay. A good, Nathan? Okay, everybody? And that's it. Right, so there's homework and quiz next class over the first two. You know, and you know, when the quizzes are pretty much just based on whatever the homework we had. I mean, if you want to go back and study anything, just look at the homework we did.